walking through things, let me tell you the plan for the day and kind of moving forward as well. The first thing I want to do is just take a couple of minutes. We don't have a lot of minutes today together at all, but to look at survey feedback. I want to follow up on the air resistance lab. If you have the lab done right now, please turn it in. If you don't, what I'm going to ask you to do is to put it away and finish it tonight and bring it in tomorrow. That sound fair? I'm not going to get them graded tonight, but I don't want you to be distracted from what we're doing in class by it. So either bring it and put it in my basket or bring it to me tomorrow. It won't be late, but I don't want to see it out right now. All right? We're going to talk a little bit more about air resistance today, and then we may get started with the next stuff. We'll just see how fast we talk. Does that sound good? Because, it's 30-some minutes today. Woo! So I just want to take a look. I'm going to freeze that for a second so that I can find my survey feedback. Here it is. Just to give you a sense of what you responded. So you guys filled out this survey last week, right? Or 2 weeks ago. I don't remember now. And I just wanted to look at this with you. I don't want to do all of the bits and pieces, but I do want you to know, number one, where your classmates are and where you are. And also to let you know that I am looking at it. I'm trying to respond to it. And if there are things that are in here that you want to tell me more about, please make some time to do that. You can find me whenever. We can have this conversation. So just to take a look kind of to see where we were at. These are just going through the questions. Reflecting on trimester 1, which things did you find most interesting? So projectile motion was the high one, and accelerating problems, those were kind of the high 2. We've got Newton's laws, and it makes sense to me. The first little bit of physics, like conversion and metric, right? It's not super exciting, but it does allow us to do these things. So that makes sense to me. Hopefully the numbers will just keep getting bigger and bigger as our year goes on. Which ones did you find the most challenging? It's interesting because this graph looks very similar to the last graph, doesn't it? Yeah. So the most interesting and most challenging are kind of one and the same. And I'll be honest, friends, that is exactly how I feel about physics too. Physics is hard. Physics is great. And it's lovely that we get to do it together and challenge ourselves together, right? That is awesome. And I like that it's challenging. And I hope that as we're going through, we're actually getting, we're feeling a building of confidence because of the hard work that you're putting in. So I appreciate that a lot. Thinking about the grading system, I've told you guys a bunch of times already this year that this is a new thing for me, but I really, really do believe in it. This is the feedback that I got about how people are feeling about the grading system. A lot of people like it, and I'm really glad. Okay, if you are part of the no category, this group here, I would love to talk to you some more. If you feel like it was just really rough this first trimester, I'm with you. Because I feel like it was rough too. I'm learning and I'm going to get better as the year goes on. So I promise that that's happening. I've already kind of started, I've been taking notes all of first try to adjust so that second try goes better. But if there are things that really don't match with what you think should be right, please talk to me so that I can help you out so that we can come to a better understanding. I'm not going to spend lots of time on these, but there were some, I would say mostly positive, kind of reading through some things that were a little bit less positive. And I think that reflects what the goal of it is. Okay. So just kind of taking a look through, you'll see your thing if you said something. As long as I do well, and I totally get that, you guys, I get that we're playing school and that's what we do. But I also want you to feel some accomplishment from actually learning and mastering things. I appreciated the comments about having the opportunity to do retakes. That's what I think is really important about this is repeatedly showing me that you know the content. Do you feel like it benefited your opportunity to learn? I'm not sure exactly how these numbers, how to interpret these numbers. So I'm going to kind of leave this one, but if there are people that want to talk to me about that, I'm super happy to answer that as well. Mostly because when I read the responses, I feel like they're fairly positive, or kind of I don't think it really helped or hurt, or I don't think it really made a difference. So I'm kind of feeling like it's generally positive or indifferent. It helped my learning a lot, blah, blah, blah. So again, part of the reason that I want to show this to you is so that you can see what your peers are saying as well. Not saying that you need to believe what your peers say, but just because it's nice to hear hear everybody's voice. Do you think that you took advantages of retakes? There were a lot of people that said yes. The next biggest one said, I just didn't need the retakes, and that's absolutely great. If you are a person that gets it on that first go round, that's awesome. That means you don't really need to do that, and that you just don't need to take advantage of it, so that's totally fine as well. Talking about extra practice, we're going to make that a little bit, we're going to tighten that up a little bit for second try to make things align a little bit better. So just kind of an FYI for that. We'll get that tightened up as well. What things were most meaningful? A lot of people said that the in-class discussions were the best. And I think that, that's kind of how it is by nature in most courses, especially in science and physics stuff. So I appreciate that. This one, I don't know why it didn't print off right, but this says discussing homework problems in class, and then review problem sets were the other two kind of high scorers there. One thing that I really want to encourage, especially in this class, my other class, when I ask for homework, are there any homework questions? We usually have a 5 to 10 minute discussion about one or two of the homework problems. That happens in here just a little bit of the time. I want to strongly encourage you, friends, if you have done the homework and you get stuck, you're confused, please bring that up, bring that out. If you don't want to do it in class because you feel like it is putting too much of a spotlight on you for whatever reason, come talk to me during Liberty time or during a time when you and I are both free so that we can find an opportunity to learn that material. Reading the textbook is not a terribly meaningful experience. And that's something that, we'll talk about, we'll work on, but I'm not gonna stress out about that. This kind of goes back to the thing that I was just saying. Did you complete your assigned homework? So I don't like that they have two blues that are very similar. This blue matches this one up here, yes, every day or almost every day. So many of you did. I totally get that if you're not, if I'm not going to take points for your homework, that some of you aren't going to do homework. And I think it's human nature, right? But I just want to remind you as we start trimester 2 that doing the homework is the best way for you to check your understanding so that you're not just walking in every day kind of blind, right? You're following up with it. So if you're struggling with things and you find that you're doing lots and lots of retakes, the best way to eliminate that situation is to do your homework. So just kind of think about that. I'm going to go ahead this try and keep the homework policy the same, but things might change eventually. But for right now, I think that we'll kind of keep it that way. The goals for next trimester, you guys can kind of take a look at these. Most of it says do more homework, do your homework all the time. So I'm just kind of reiterating exactly what that was. Becoming more engaged, reviewing more, doing homework, blah, 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 and making sure that you're doing the best on your quizzes and trying to keep your grades up. So that's pretty much it. And then that's it. But again, I just wanted to kind of show that to you, give you a sense of where your peers are. Do you guys have any questions or follow-up thoughts that you want to share right now about that? It pops into your head. If something does come up or you have something in your head that you would love to talk to me about, but you don't want to do it in front of everybody, please come talk to me at the end of class or whenever. Let's have a chat so that we can feel good about this going into second trimester, because there's, it's a lot to do and we're just going to keep cruising. Okay. So we're going to move on to air resistance today. I just want to follow up. We're not going to spend a lot of time, but a little bit here. So last week, right at the beginning of the week, we dropped coffee filters and we watched them fall. It was very exciting watching coffee filters fall. And talk to me about a coffee filter versus a frog. Who hits the ground first? Frog. Why? Because he's what? Say it again. Takes it longer to reach terminal velocity. What does terminal velocity mean? The highest velocity that it can hit. Yeah, and terminal velocity is dependent on what has to be present in order for a terminal velocity to be a thing. Air has to be there, right? Okay. So we kind of talked about this last week, but I didn't get a chance to show you some evidence of this. Okay. So I've got a couple of quick videos to show you. This first one is the most famous example of this. Can I have you go flip the lights off, Cassidy? Thank you so much. So this is the video from the Apollo mission. Okay, so I'm gonna.
And penetrometer drum in the ETD.
Not quite yet. I haven't put the silver line in yet, but I will shortly. I want to watch a good picture there. I've got,
Beautiful picture, Dave.
well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of the gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather, or a falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Listen, Mr. Galileo was correct in his findings.
That's horrible noise.
Superb.
All right, it's like the outtakes. That's cute. What's that? So my first question for you is there gravity on the moon?
Yes.
Yes. Absolutely, there's gravity on the moon. There's a gravitational force between any two objects with mass, right? Okay, so I stand on the moon, I have mass. The moon is a thing that has mass, so there's going to be a gravitational field between the two. Any two objects that have mass have a gravitational field between them, right? And a gravitational force between them. So absolutely there is gravity. What did you see in that demo? A rather expensive demo to put on, right? What did you see? What'd you see, Lily?
They felt the same rate.
They fell at the same rate, right? They being what?
The two things.
The two things. The feather
Yeah.
and the hammer, right? Which is like the frog and the coffee filter. Okay? The frog and the coffee filter, or the hammer and the feather on Earth are going to fall at the same rate? No. So is it because they're on the moon that this happens? Is it because they're on the moon that they fall at the same rate? Or what is it that we're missing? Any idea? Yeah, air. So here's one more video. I like this one a lot too. What's that?
And
It's a vacuum. There's nothing there. There's no air. So the answer is nothing, right? It's weird to think about because, you have this conversation, right? Like, I don't know if I put it up here before, but like the glass is half empty, glass is half full, right? And the scientist says that the glass is completely full, just half with water and half with air. Okay. But if you take a cup to the moon and you set it there, you can't have that same argument, right? It would be half filled with water, half empty with water, but there's nothing above it. There's no air. There's just no nothing, which is why we can't live on the moon without having those helmets connected to those big tanks. What's that? Tell me more about what you mean. I'm not understanding.
Marshmallows in a vacuum if they like expand.
Yes. So yes, I guess they would.
It's like if you took your helmet off of you.
Well, there's an issue with your lungs, right? That your lungs would actually, because they take in the air, they actually would collapse in on themselves, which would be a problem for that whole like breathing. I'm not a biologist, but it's my understanding that that's a necessary function for life. But yes, yeah. So can we do this on Earth? The answer is indeed we can. This is another. I like this video a lot. It's kind of interesting. Same kind of deal here. Oops, can I play it?
it does that by pumping
Oops.
out.
Hold on, let's go back to the beginning.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and It does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left.
2 grams of air in that full
And it's
space.
kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems. And that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now, in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
We dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
So this is on Earth, right? This is an Earth's gravitational field. So it's not that the moon is special.
Look at that.
They came down exactly the same. Wow.
Look.
Exactly.
So these are like PhD physicists,
Exactly
right?
right.
Like they should know that this happens, but to actually see it is, it's just mind blowing.
Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently.
Think about this. This is kind of mind blowing.
The happiest thought of his life was this. The reason the bowling ball and feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the earth. So he concluded they weren't.
What? So that's weird. So there's some relativity in there for you to kind of like give you a little brain teaser, right? So the question there, can you hit the lights for me again? The question there is, are the ball and the feather falling, or are they sitting still and everything else is moving the other way? We don't really know, right? It's all kind of a game. It's all kind of funny and weird. So anyway, just some things to think about there. Questions so far? Are we doing okay? Yeah. So I'm going to throw one more thing at you, and this is the piece that puts that all together. So these should not have been a surprise to you. These should not have been like too mind-blowing, although they're kind of nice to see, right? To like actually get verification that what we're talking about is right. We're going to work through a problem that may take us a little while. I want you to get a piece of paper out because it's going to ask you to make some predictions. So I want you to make some commitments here. This is not like big, scary note stuff, but just some thinking to do. You don't need to have a long conversation while you're getting paper out. Paper does not require vocal cords. Thank you so much. So as you watch this video, I'll pause it a bunch of times because that's what I do. I want you to engage with this. The guy that does this is a very famous physics teacher, which sounds really weird, right? Like a famous physics teacher, what? But like, actually, he has written lots of textbooks and things like that. And also is a very good drawer. He was actually a cartoon artist turned physics professor, right? Because that's a thing. And yeah, so anyway, we'll give this one a look. And the music is cute.
Here's a problem that involves some insights and nicely illustrates Newton's second law. Susie Skydiver dives from a high-flying, hovering helicopter. As she falls faster and faster through the air, how does her acceleration change? Does it increase, decrease, or remain unchanged?
Okay, so I want you to write that down. That's question 1. So you can just write skydiver, and I would write down the how does her acceleration change? The question is, does it increase, decrease, or remain unchanged? I want you to make a prediction. Write that down. Based on what you know, we are including air resistance, right? That's the whole point of our conversation today. So think about that. How does her acceleration change? I'll give you just a couple seconds to talk to your teammates. So fast. So I want you to write something down on your paper. Either that it increases, that it decreases, or that it remains the same. This is not a test. It's just we have to think about and commit to things before we move on.
Yeah.
All right, I'm going to keep going. Maybe.
Let's first identify the forces that act on Susie.
Hey, because that's what we do, right? That's how physics works.
There's always the force due to gravity. Agree?
Agree?
We can call this mg.
Agree. He doesn't write it quite the same way.
If this were the only force on her, she'd be in free fall, and her acceleration would be g. But she's not in what we physicists call free fall, not with air resistance. Let's let R be the upward friction force of air resistance, opposing her downward plowing through the air.
I don't know why it says R, but we'll just go with it.
Now that we've identified the forces involved, and since the question asks about acceleration, we begin this problem with A equals. And here's where Newton's second law applies.
We okay with that?
Newton's second law guides us to the net force on Susie, which is mg minus r. We'll call the downward direction positive. Although mg remains constant, air resistance r changes. The faster she falls, the greater r becomes. And the greater r becomes, the less net force becomes. Are you
guys okay with that? The faster it goes, the air resistance is going to push up more. The bigger the negative piece, the smaller the total.
Increased net force means a decreased acceleration. So we have the answer to our question. As she falls faster and faster, air resistance R increases, making mg minus r smaller, resulting in a decreased net force and a decreased acceleration. Problem solved.
But wait, there's more.
We can go further with a bit of algebra and isolate G.
Algebra.
Note how each step dictates the next step. Equations clearly guide our thinking.
Are you okay with what just happened there? So he just took this M and split it into two fractions. There's an M on top and the bottom of this one, so that just makes it less just a G. Okay, so that G is going to be constant. He'll talk some more. Yeah.
Why doesn't it accelerate?
What's that?
Why doesn't it accelerate?
She is accelerating. That is her acceleration.
Oh, okay.
Yeah, that is her acceleration. So her acceleration is equal to this. And as R changes, then A is going to change. Yeah.
Note that if R equals 0,
There you go.
the equation reduces to A equals G, free fall. Does this make sense? I hope so.
Are you guys okay?
Note that if
You're not responding. Are you okay with that or
Yes.
no? Jacob says yes. Huh? You're not okay. Ethan, tell me why you're not okay. What's wrong? What are you upset about? You're okay. So this one I usually would write as like the force of air, right? And so they're saying that if the force of air resistance is 0, meaning there is no air resistance, if that thing is 0, then all you have left is the G. And if all you have left is the G, then that's how fast she's going to accelerate. So this is the world that we've been living in for first trimester. And then remember, right before Thanksgiving, I threw this at you and I was like, ha, air resistance, ha, right? And that's where it changes a little bit. And that's not only going to change the force, but it's also going to change her acceleration. Yeah.
If R builds up to equal her weight, mg,
Oh,
then acceleration reduces to 0.
whoa. Did you catch that one? What did he just say? If the air resistance force equals the gravitational force, what does that do to the net force? If the air resistance force is the same as the gravitational force, what does that do to the net force? Makes it 0. It cancels it out, right? And then the way we say it, if the net force is 0, what does that mean about the acceleration? Oh, it's 0. He's just saying it a little bit of different words, but it's the same thing. It's the same idea. Come on. There you go.
Yum on that?
I don't know.
With 0 acceleration, does this mean her falling velocity is 0? No, no, no. It's her acceleration that's 0, not her velocity.
He's funny.
At this point, should have reached what we call her terminal speed or terminal velocity. Reaching terminal velocity means 0 acceleration and she falls at constant velocity. After she opens her parachute, air resistance R will be huge and she'll slow to a lower terminal velocity. Let's shift gears. Our question about Susie's acceleration gets mixed answers from students in general. But what if the question instead asked about air resistance? Susie Skydiver dives from a high-flying, hovering helicopter. As she falls faster and faster through the air, how is air resistance affected?
Write that answer down.
Does it increase, decrease, or remain the same?
So as she falls faster and faster, what happens to her air resistance?
This question gets more correct answers from students. All you need to know is that air resistance is greater at higher speeds. Or let's suppose the question asked about net force. She dives from a high-flying helicopter, and as she falls faster and faster through air, how is net force affected? Does it increase, decrease, or remain the same?
What's your answer to that one? As she falls faster and faster, how is the net force affected? We've kind of talked about it already, but just make sure it makes sense to you. Check with your table mates. Do they agree? That was a very astute answer. All right, you ready? What's going to happen? What do you guys say? How does the net force change? Decreases? Sure. Magnitude gets smaller?
Can you see that this question is one step in difficulty greater than asking for air resistance? That's because there are two concepts, mg and r. But again, the equation guides you to an answer. And can you see it's an additional step to ask how acceleration is affected? Do you think that your friends who get the initial question about acceleration wrong would get it wrong if they were first asked separate questions about air resistance and net force?
That's a good question.
Some people don't like the idea of grasping for an equation when answering a question or solving a problem, but that's not me. I like the idea of grasping for an equation, one that contains what you're looking for. Equations are shorthand statements of how concepts connect to one another. Equations are more than this. They are guides to thinking. So if a question or problem asks for acceleration, begin the problem by writing A equals and go from there. If you're asked for average speed, start with V equals. Oftentimes that's the hard part, getting started. Or if you're asked for the force that such and such does on something, then just write F equals and go from there. Let me leave you with a question. Susie's cat falls from the top of a 10-story building and reaches terminal velocity before reaching a safety net below. Will the cat's landing speed be different if it fell from 20 stories high? Defend your answer.
Answer that question. Talk to your table mates. Go, go, go. What was the question? So if the cat falls from 10 stories up and reaches terminal velocity before it hits the safety net, how would that terminal velocity compare to if it dropped from 20 stories up? How would the terminal velocity compare is the question. What'd you guys say? Why did you say it was the same, Grace? The terminal velocities are going to be the same regardless, right? It's just going to travel for longer at that terminal velocity. Yeah. Cool. Is that all right? Yep. Okay. So there's your air resistance stuff. We're going to stop there. You can put your stuff away. We will start the next unit tomorrow.